Okay, good day. This is AP Calculus. I am Mr. McCulley, and this is the presentation on section 1.3, evaluating limits analytically. Let's get right to it. So today we are going to use the evaluate a limit using properties of limits. We are going to develop and use strategies, plural, probably should have plural there, for finding limits, and we're going to evaluate different limits using the dividing out technique, the rationalization technique, and the squeeze theorem. So what are all of these things? So my big notes here, I'm going to start with a bunch of properties of limits. You definitely want to commit these to memory, but before I get started, I have to reiterate that the rules that we are about to discuss involving limits are all based on the limit process that we learned in section 2. They are intended only as shortcuts, but not as a proof. So when they say find that something has a limit, you can use these shortcuts to find the limit. But when it says prove that that's the limit, you have to use that proof concept. So basically what happened is they didn't always want to go through that delta epsilon process, so they proved in general some basic rules. And so as a for instance, just the easiest ones is that the limit as x goes to c of some constant b is just b. And that one is probably the easiest one to talk about, because let's say I do this. I get the good line here. Oops, didn't want that. Let's smooth that up. Okay. And let's me call this c. What is the limit of the function y equals b as I come in from the left and from the right? Well, it's just b. Um, the limit of x, well, x is just the function that is this linear equation that goes through the origin that has a slope of 1. Well, at c, that's going to be whatever c is. And then if I raise it to a power, it's just going to be that value as well. All right, so let's move on to some other properties. These are a little bit more complex, but they're not too difficult. So if I let b and c be real numbers and n be a positive integer, f and g are functions with the following limits. So b and c are real numbers, so any real number that you could think of. C is a constant, and f is some function, and when I want to find the limit of that some function as x goes to c, it's L. Similarly, with some function g, as I go to c, the same value as in the previous function. When I find that limit, it goes to k. All right, so let's talk about these properties here, and I'm going to do some examples as we move forward. Um, So what is the limit as x goes to c of some constant times our function? Well, I can bring that constant out, find that limit, and it's just the constant times whatever the limit of the original function is. The limit as we add or subtract two functions, well, that limit is the limit of the first function plus or minus the limit of the second function. If I do a multiplication for the limit as I go from x to c for both the f function and the g function, then it is the value of the limit for the first function times the limit of the second function. Similarly, when you divide, dividing doesn't change anything. It's the limit of the top function over the bottom function, provided that that bottom function doesn't have a limit of 0. Now again, you can have a limit of 0. And then finally, the limit of some function raised to the n power is just the value of the limit raised to the n power. And again, I have a couple examples that I want to show you a little bit later. Okay, rules, mathematical definition. These are all on page 60 and 61 of the textbook, I think. It's pretty close. The limit of any polynomial function at c is the value of the function at c. Now that's for any polynomial function, and hopefully we all remember our definition of a polynomial function. This is called direct substitution, and direct substitution works an awful lot. It is, again, It is a shortcut rule for finding a limit if you know what type of function you're working with. The limit of any rational function at C is the value of the function at C provided that the denominator is not 0 at C. So we can find a limit if it's not undefined. And then again, we're just direct substitution. The limit of a radical expression at C is the value of the function of the delete provided that C produces a positive value under the radical for even roots. So again, if the value at C is going to provide an imaginary, then we can't use that one either. And then the limit of a composite function. This is a little bit different than the other ones, but it is, if you take the limit of a composite function, then it is the limit of the inner function, and then whatever value you get for that inner function, you plug it into the outer function, and then make that calculation. And then the value of any trigonometric function at C is the value of the function at C provided that C is in the domain of that trigonometric function. Okay, moving on. Okay, now for the squeeze theorem. And before I get into the squeeze theorem and how to use it, generally it's basically this. And we're going to use a little visual representation to talk about it. So let's say I have one function that I'm going to call, we're going to call this f of x. And I'm going to have another function, and we'll call that other function. You know what? Let's do it this way. Let's go back just a little bit. We're going to do it right here. We're going to put this point C right here. And I have this other function. We're going to call that one g of x. And then I have a third function. I'm going to do a better job of hitting this right. Oops, come on. Maybe if I make it a little smaller, my thickness, I'll make it a little easier. Right there, like this. Let's call this h of x. Now, what the squeeze, let's say, as a for instance, we do not know what the limit as x goes to c of h of x is. We don't know. But what we do know is that we know that f of x is always greater than or equal to g of x for all x. And we know that the limit as x goes to c of f of x is some value L, and the limit as x goes to c for g of x is also that L. If h of x is always between these two functions, then what we can say is that the limit as x goes to c of h of x, since these two are equal and h is always in between the two, then we can make the conclusion that the limit as x goes to c of h of x is also L. All right, so let's talk about this limit right here. And so I'm going to give you an idea about the squeeze theorem to figure out a limit. We want to do this. So if I say, what is the limit as x goes to 0 of sine x over x? Now, if I go to 0, the sine of 0 is 0, and when you let x go to 0, it's also 0. So I get 0 over 0, it's undefined. So I don't really have a good method for solving this particular value. But let's look at it a different way. Now, you might be looking ahead and seeing, well, there's no sine x over sine x on any of these, but we're going to get there. Trust me, okay? But think of it this way. I've got these 3 triangles, okay? Well, actually, I've got 2 triangles and an area of a sector. So I've got this big triangle right here, and if I want to find the area of that big triangle, remember the area of any triangle is a equals 1/2 base times the height. Since this has a base of 1, 1/2 times 1, there's your base. And if you have this angle here, x, then the height, and if you need me to do this in class, I will, but excuse me, you can manipulate this triangle so that the height is equal to just tangent x. So 1/2 times 1 times tangent x is tangent x over 2. Now, you see this little curve that I have here in blue? Well, think of this as a section of a circle. It's a sector. It's a piece of the pie of a circle. And if you remember from pre-calculus, the area of the sector is 1/2 r theta. And so our theta is x, 1/2 is there, and our r, because again, this is a portion of a circle, will be 1 here, and it would also be 1 here. And then finally, the area of this little triangle, this little distance right in here, this smaller one, is going to be, again, it's 1/2. The base we see to be 1, and then to find the height, which would be this little red dot, we would go sine x, and again, because this is a section of a circle, this would be 1, and this distance would be 1. Now, clearly, no matter what your value of x is, this big triangle is always going to be bigger than the sector, which will always be bigger than this small triangle. All right, so we have a squeeze theorem function. All right, so now, again, let's step back. We're trying to get to this. We want to figure out what this limit is, and so we want to keep everything the same. So what we're going to do, and we're trying to get this in the middle, sine x over x. So we're going to do a little bit of manipulation. So we're going to multiply by 2 over sine x. Well, if I multiply by 2 over sine x here, I'll get tangent x times 2 over sine x times 2. The 2's cancel. And if I go 2 times x, I get 2x, and then 2 times sine, I get 2 sine x. The 2's cancel again, and I get x over sine x, which is close to what I want here. And then when I go 2 times sine x over 2 times sine x, I get 2 sine x over 2 sine x. All right, so we'll multiply by that. Let's see here. So I get I'll get, let's start over, get my correct, that's what I want. So I get tangent x over sine x is less than or equal to, it'll be x over sine x, which is less than or equal to 2 sine x over 2 sine x. Now, if I take the reciprocal of everything, it's going to flip, and then because this one's bigger, this fraction is bigger than this fraction, for that to be true, the denominator or the numerator of this one has to be bigger than the denominator, or actually when I do the flip, because of the property of ratios, when I do the flip, the bottom of this one has to be bigger than that value. So I'm going to take the reciprocal, and then I'm going to reorder. So I'll get 2 sine x over 2 sine x. This one stays in the middle. It's still greater than or equal. I'll get sine x over sine x. And then that'll be greater than or equal to, it'll be sine x over tangent x. That's me taking the reciprocal and then reordering. Did I do that right? Nope. Nope, that's wrong, because I need this to be the reciprocal of that. So it should be x on the bottom. Well, let's see what we get here. Just as a little aside here, I get sine x over tangent x. Remember that tangent x is sine x over cosine x. And so this would be a sine x over 1, that's this top fraction. And since I'm dividing by a fraction, it would be cosine x over sine x. So those cancel, and it leaves me with cosine x over 1, which is just cosine x. So back to this one. Let's go back down here. And so I get a 1 here because I got 2 sine x or 2 sine x, that's 1. I'll get less than or equal to sine x over x, and then we said that this one was cosine x. Yeah. All right. So what is the limit as x goes to c of these values? Well, we already know that the limit of a constant is just a constant. That's just 1 less than or equal to sine x over sine x, and we can't figure that one out. Now this one though, this cosine, we can do a direct substitution because we know that the limit as x goes to c of cosine x would just be the cosine of c. And I'm sorry, I made it a little bit of a mistake here. We're trying to find that limit as it goes to 0. So to make it 0, and again, it doesn't change this one because it's a constant, so it's always 1. And so this one has to be 1. Now, since 1 is less than or equal to something less than or equal to 1, for that thing to be true, and again, I screwed it up. I guess you guys are probably sitting there laughing at me. And I hate making that mistake. Since I've got 1 on the left and 1 on the right, what's in the middle, if this is greater than or equal to, and these two are equal, well, then this one has to be 1. So we can conclude that the limit as x goes to 0 of sine x over x, that also has to be 1. All right, let's move on. Now we're here to some examples. Okay. Let's find the limit as x goes to 1 of x squared minus 2x plus 3. Well, this is a polynomial. I don't even know why I have an S there. In fact, it's not just a polynomial, but it's a specific polynomial, quadratic. It's a quadratic equation. And we had a rule back here, the limit of any polynomial at c is the value of the function at c. So instead of going through that whole big process here, we can just say that this is going to be the same as 1 squared minus 2 times 1 plus 3, which would be 1 minus 2 plus 3, which is 2. So that limit is 2. All right. Given that the limit of f of x as x goes to c is 27, find these limits. Well, what we're going to do is we're going to use a bunch of these properties here that we did in the beginning to come up with those values. Now, our current function is a composition of functions here, so we're going to actually figure those out. And nope, that's not the right one. There it is. And so this thing right here is the composition of or this expression here is the composition of the function f of x and the 1/3. So I could rewrite this as the limit as x, and again, you don't have to do all of these, but I'm just trying to show it, f of x all to the 1/3 power. Now we know what the limit as x goes to c of f of x is. It's 27. So we can just replace that 27 right there to the 1/3 power. And 3 times itself is 3 times itself 3 times is 27. So the solution to this limit is 3. Here it says what is the limit as f goes to c of f of x over 18. Now we can do this a couple of different ways. My favorite way, or the way that I would probably see this most, is using this first expression here. I have a function that I know times a constant, and that constant is 1 over 18. So I would rewrite this thing as 1 over 18 times the limit as x goes to c of f of x. Now I guarantee this is not the only way to do it, but I can now replace this thing with the 27 that I was given at the beginning and say it's 1 over 18 times 27. That gives me 27 over 18. I can take a 9 out of both of those and say it's 3 over 2. All right, moving on. Find this particular limit. Now, this is a rational function. And so the rule that I'm looking at here, the limit of any rational function at C is the value of the function at C, provided that the denominator is not 0 at C. Well, clearly, if I let this be equal to 0, I get 0 on top over 0 on the bottom. So that doesn't work because that is an indeterminate form. So one thing that we can use is called the, did I do it yet? Oh, we're using the dividing out technique in this particular problem. So what we're doing here with the dividing out technique is I see that each of these terms has a factor of x squared. So I'm going to take the limit as x goes to 0. I want to factor out an x squared. So an x squared times, it'll be x squared minus 5 over x squared. All right. And this thing, now my x squareds cancel. So the one thing I want you to understand with the dividing out technique is what I'm doing here. This is a new function with the same limit. All right, so when I go down here and I say the limit as x goes to 0, if I cancel those two x squareds out, I get x squared minus 5. Well, this function is defined at as x goes to 0. But clearly we can say that the original function was undefined. So these two functions can't be the same. It's their limits that are the same. And then I can just say it's just negative 5. Well, you could check that. You could check that with your graphic calculator if you wanted to. All right, last one, finding the limit. So I'm going to let the limit as x goes to 0. I've got an x on the bottom. If I plug in 0, I get square root of 2 minus square root of 2 is 0 over 0. Again, indeterminate form. Unlike the last one, I can't divide. These don't cancel, and hopefully calculus students don't say, hey, we just cancel out the x. You can't do that. So this time we're going to use the rationalization technique. So rationalization technique. CH. I think that's spelled correctly. Let's see. rationalizing. I have one more. Two more. Tionilizing. Huh. Hopefully that's right. All right, so here I'm going to multiply by funky 1. And that funky 1 is going to get rid of, remove radicals in the numerator. And hopefully that'll help us out. And so for me to remove the radicals here, I'm going to use my funky 1 that is my conjugate of the numerator. So I want to say it's 2 plus x, now plus square root of 2, and then it'll be 2 plus x plus square root of 2, and we're just going to use that. And remember, so note a plus b times a minus b is equal to a squared minus b squared. So this thing becomes, and again, I'm not taking the limit, so I have to write the limit. So this is my a, here's my a, here's my b, here's my b. So this is going to be 2, it's going to be 2 plus x minus 2 all over x times the square root of 2 plus x plus square root of 2. And so again, I haven't evaluated the limit yet, so I have to write the limit. Going to 0, I get x over x times square root of 2 plus x plus 2, and then those x's cancel, so I am still using a dividing out technique a little bit here. The limit as x goes to 0 of 1 over square root 2 plus x plus 2. And you might be saying, well, hey, Mr. McCulley, I still have an x in the denominator, but this x in the denominator does not cause, oh, made a mistake, sorry. I lost the square root, so I need a square root there. Sorry about that. You might be saying, well, I still have an x that's 0, but when I let this x go to 0, I don't get an undefined like I did in the original one. When I let x go to 0, and now I'm evaluating the limit, so I don't have to write the limit anymore. When I let x go to 0, I get 1 over square root of 2 plus square root of 2. And that leaves me with 1 over 2 square root of 2, which we should probably rationalize again, though I probably would accept that as a final answer, but I definitely wouldn't be on the AP Calculus as a final answer. They would rationalize that. Square root of 2 over square root of 2, they'll give me square root of 2 over 4 as my final answer. Well, folks, that's all I got. It's been a good long one, 26 minutes. That's probably pretty long. You're tired of hearing me talk, so have a good day, and I will see you in class. Goodbye.